I'm going to spend this hour in a very, very relaxed and patient exploration of AES. First of all, we'll look at AES encryption, how it works, and like a really, really intimate view of AES, how it works. And then we are going to do a DPA. And DPA from beginning to the end, and you will get to experience it yourself. And as I told you, I will release all the source code as well. So, Matlab environment, live lab. Next year, God willing, we will have this in a Colab notebook. Somebody is working very hard on it right now. So I'm going to start by including some Matlab scripts, which I prepared ahead of time. I just want to make sure. Change. So these are a bunch of scripts which implement all sorts of AES operations. You know, sub by shift from miscolumns. One of them is actually there are tricks in this implementation, because I actually wrote an 8-bit microcontroller implementation of AES, which has power consumption leakage. So usually Matlab doesn't leak power consumption, but I went ahead and I'll show you. You know what? I'll just show you. So the first thing I want to show you is how AES works. So here are two plaintexts, and they are 16 bytes long, and they have a single difference between them. You see, this one says 6, and this one says 7. And now I'm going to show you the Hamming distance between them. So the Hamming distance is equivalent to the Hamming weight of the XOR, right? So let's do this. And indeed, what is the Hamming distance? It is 1. Tell me, is the font too size? Is the font size good? Do you want it? Do you want it? I can't do polls, unfortunately. Font size, okay, great. This is one thing which is nice about remote teaching. Everybody is sitting close to the screen. Usually, I have to have like 72 points. But I wonder what YouTube will do out of it. Okay, let's keep going. So I'm going to generate this super cyber califragilistic key. This key is also 128 bytes bit, and I'm going to define some constants. So now I'm going to encrypt these two plaintexts, plaintext 1 and plaintext 2, using the same key. And you saw that the Hamming distance between the two plaintexts was 1. Can anybody guess what is going to be the Hamming distance between the two ciphertexts? A lot. Yeah. But over 9,000? Throw a number. No. Give me a guess. What is going to be the Hamming distance between the two ciphertexts? 64. Right? 128 says Gil. 64 says Gil. Okay. So you're guessing 64, and why are you guessing 64? Because there is something called the avalanche property. The avalanche property means that 1 bit of the plaintext is supposed to affect all of the bits of the ciphertext, right? And of course, flipping all of them is meaningless. That's not good at all. But an average of 64, binomial around 64, a bit more, 62, 70, something like that. So now let's see, let's run this one more step. And you see that the plaintexts are very, very similar, but the ciphertexts are very, very different. What is the Hamming distance? Well, it is 52. So 52 is close enough to 64. Close enough, yeah, also for me. So now we're going to decrypt, and just to make sure the decryption was okay. I'm not very worried. Yeah, so the decryption again worked well, just to make sure it's decrypted. So this is. I hope this is stuff you already saw another places. But here is something tricky and new. I wrote a function. Actually, when I was a PhD student, I wrote this function. It's AES 8-bit encrypt and leak. So it's going to do encryption, but it's also going to give me a leak. It's going to tell me, it's going to give me a vector, which is all of the evolution of the state through all the subrounds. So this is 40 times 16. It's only the subrounds. I'm not doing mixed columns here. So the first 16 bytes are going to be the plaintext. The last 16 bytes are going to be the ciphertext, but I'm going to give you all of the leaks in the middle. And now if you look at this function, I can just open it for a second. Wow, this is pretty small. Can I make it larger? No, I cannot. Control Plus doesn't work in this editor. Too bad. So I'll just, you know what, you have good screens. You have like HD screens. I'm not worried about you. I'm just going to, so you see encrypt. Let's look at encrypt. I have, I add round key. I add the key actually, add secret key. And then I have 10 rounds of, you see, subbytes, shift rows, mixed columns. Subbytes, shift rows, mixed columns. How does subbytes look? Well, it's just a lookup table, okay? How does shift rows look? The logical move, okay? It's just moving. How does mixed columns look? Mixed columns is a bit tricky because it's an 8-bit implementation, but this is mixed columns, and as you see, it leaks a lot, but it works. Believe me, I tried it on the least test vectors. So what's important about this, that I don't just get the ciphertext, I also get the state evolution. We're going to look at it. So let us encrypt and leak plaintext 1 and plaintext 2, and let us look at the result. So the function subplot is going to give me like a panel for 1 and a panel for 2. Let's see how it looks. This warning is good. It means it's going to draw. So this is a bit small. Right. So this is the evolution of the state, beginning at the plaintext and ending at the ciphertext. Now, immediately you see that the plaintext they're very similar. In fact, I don't think you can see this one bit difference in the state. You can also see, if you're a bit hackerish, that they're using only like greens and oranges. That's because it's using ASCII and it's not the entire character set. So even from that you can learn. But you can see that pretty quick. They look very, very different from each other. Of course, that's because AES is a good cipher, and in the end, we need to get completely different ciphertext. So now I want to show you how the difference is evolving. And this is actually, I think it's very, 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 very cool illustration of the subround of AES. So this is the difference between the two ciphertexts. And I think it's a very, very nice way of understanding the internals of AES. So the middle is the XOR of the left and the right. And red is, of course, here. So the first round, the operation is, what is the first operation you do under AES? Does anybody remember? Add key. Yeah, you do add key, you XOR it with the secret key. Now, does this operation affect the difference, the XOR of the two encryptions? Now, if you think about it, I'm XORing the same value on the left and on the right, and this means it has no effect on the difference between the traces. This in the middle, you call some people call it the differential. So XORing a value has no effect on the differential. The next operation is, what is the next operation? Subbytes. Very good. Okay. So subbytes takes this value, which has a difference of Hamming distance of 1, and makes now what is the difference between the two? It's going to be subbytes of 1. So now there's a 1 byte difference. It's a little orangey, just because subbytes of 0 or subbytes of 1 is a low number. What is subbytes of 1? Let's see what it is. How is the function called? Subbytes? It's S box. I don't remember I don't remember. So so this is the difference anyway. Let's go back to the figure. So there is only 1 byte which is different between the two, and it's this byte. What is the next operation of AES? Shift rows. Very well. Shift rows. So what does shift rows do? You see that this little difference is shifted, and it goes here. So still, the state is completely identical, other than that little difference, it will just shifted. Now the next operation, what is it? Mixed columns. Very well. Okay, so mixed columns mixes the 4 consecutive state bytes here, which are in the same column, together. So now you see that this little change is propagated into 4 bytes, but only these 4 bytes. Okay, next operation, what is it? After mixed columns? Add the round key, not add key, but add round key. And add round key, again, it's a linear operation, doesn't affect the differential. So the difference stays. I added the same round key to both sides. Now, what is the next operation? Subbytes, right? So subbytes, and now you see that these 4 bytes got changed into 4 completely crazy different bytes. Next operation, shift rows. You see now the shift rows. Now you see that these values were distributed 1 into each column, and the next operation, mix columns, already propagated the change. And now after mixed columns, you see after 2 rounds, this 1 bit change has affected all of the bytes of the state. Yeah, now all 128 bits of the state. Yeah, but after we did mixed columns, it affected everything. So why isn't AES 2 rounds? Because there are some cryptanalytic tricks that can work on 2 rounds. You need more than 2 rounds. How many rounds exactly do you need? That's a nice question, but 2 rounds are not enough. But after 2 rounds, each bit of the state is a function of all of the bits of the plaintext. And as you see, this 1 bit change was propagated to the entire state. Right. So anything else I want to show you? Now I can also show you the Hamming weight of the difference. Just to see the Hamming weight. So Hamming weight is between 0 and 8. And you see it's going to look a little different. So what I'm showing you now is, I want to do this properly. do it properly. Let's try this. Okay. So what you see here is the evolution of this change, of this difference between the two encryptions. So you see in the first sub-round, the difference was only one bit was changed. I changed one bit. And you see, add round key didn't affect this difference. And then sub-bytes made it grow a little bit. Shift rows didn't change it. Mixed column made it grow. And then sub-bytes made it grow again. And then you see after in the second round, you already are hovering. You see you're hovering around between 60 and 70 until all the way you got to like yeah. In the end, we got 52. So you see the evolution of AES. So now I hope this was a nice exploration of the internals of AES. And now we can go on and do